Hello everyone, welcome to the new tutorial, which is about the thermal stress analysis of intersecting pipes. Here we right click on the parts container and select import. We import the .sat file uh, for the pipe and press on OK. Over here, uh, we press on OK as well. And this is the geometry that we have to work with. So over here, we go on to the shape, cut and extrude. And to select the plane, uh, we select this one and then we choose the option horizontal and on the top. So this is the edge. So now we are in the sketching domain and let's zoom it out a bit. We use this create lines connected option, and over here through the center we create these lines. Now we'll press on escape and done and extrude it through all. So now you can see that the geometry has been cut in half, and we are going to repeat these steps for a different face. So again, we go on to the shape, cut, extrude, select this face, and now we'll select this edge. What we do now is we use the same tool again, the create lines, and through the center again, we create these lines so that we can extrude it later. Press on escape and done. Now again, we need to extrude it through all. Press on OK. So this is the geometry that we are going to work with. Now going on to the tools in the main menu bar, and the option is geometry edit. Over here in the face category, we choose replace. And so now we actually want to replace or basically finish the fillets. So let's rotate it a bit. So this is the first fillet. Choose the option individually over here, and this is the first fillet. Rotate it again. So press on shift and select this second fillet and the third fillet. Now we need to toggle on the extend neighboring faces and press on done. You can see the fillets have been removed, and the adjacent faces are automatically extended by the abacus in order to fill the gaps. So this is the final part geometry, and press on cross, and we can rename the model as thermal. Press on OK, and the model, let's save the model as well before proceeding and name it as pipe intersection. Press on OK. Now we go on to the materials tab, double click, and over here we name this as aluminum. And first let's enter the thermal properties. So go on to the conductivity over here, and we need temperature dependent data. So select this and put the conductivity as 204 at 0 degrees, and add another row afterwards, and over here put the conductivity as 225 at 300 degrees. So we want to enter the specific heat as well. So the value is 880, and the inelastic heat fraction over here should be 0. Now let's add the general properties, and firstly we enter the density as 2700. Now the mechanical properties, and let's put the Young's modulus and Poisson's ratio. So the Poisson's ratio is 0.33 and Young's modulus is 6.9 e to the power 10. So uh, let's also add the coefficient of expansion, which is 8.42 e to the power minus 5, and temperature dependent plasticity. So over here, now first toggle this on, use temperature dependent data. So now we have three columns over here. So right click on the stress and choose the option read from file, and this is basically the file uh, .inp, this one, and press on OK, and press on OK over here as well. And you can see the values for stress, strain, and temperature. So there are a total of 27 values, and press on OK. Next, let's create a section and keep everything as it is. Just name it as aluminum section and press on continue. Assign the section properties, section assignments. So select the entire part, press on done, press OK. So now let's go on to the instance in the assembly module. Double click on it, choose the part as instance type as independent. There's only one part, choose that, and press on OK. Next, let's create a step and double click on steps, and over here choose the step as heat transfer, the type over here, and press on continue. In this dialog box, the time period is 200. Initial increment size should be 1, and toggle this on, put the value as 0.5, and the maximum allowable temperature as 10, which is basically the change per increment. Press on OK, and over here go on to the output, and over here go on to the restart request and put the frequency as 5. Press on OK. Now we need to add the surface film condition, and in the model tree we double click on the interactions over here. In this dialog box, choose the surface film condition as the type of selected step and press on continue. So now select the outer surface, rotate it, select this outer surfaces, selected all the outer surfaces. Now let's press on done. In this dialog box, put the film coefficient as 50 and the sink temperature as 20 and press on OK. Now the fluid temperature on the inner surface is supposed to be time dependent, and for that we actually double click on amplitudes, and in this dialog box uh, keep the type as tabular, press on continue, and in this dialog box uh, choose the time and frequency, so it's 0 and amplitude should be 20. For the next value it's 10, and for 100 need to add another value, So insert row and put it as 200 and 400. So press on OK. Now uh, go back to the interactions and create another interaction, which is for the inner fin condition. So press on OK again, rotate, rotate it so we can choose the inner surfaces, shift and this. So these are the inner surfaces. Press on done. In this dialog box, put the film coefficient as 1200 and the sink temperature as 1 degrees and amplitude curve should be amp1. Press on OK. Now let's put the initial conditions and double click on predefined fields. In this dialog box, choose the step as initial and go on to the temperature category. Press on continue and we select the complete model by by dragging the mouse across the viewport and press on done. In this dialog box, put the magnitude as 20 and press on OK. So now we have to partition and mesh the part, and in the model tree we expand the uh, instances container and this one and double click on mesh. So now we are in the mesh module. So from the main menu bar, go on to the tools and partition. And over here in the type as cell, choose extend face. So we have to partition the end region uh, like this. Let's rotate it. So we select this face, choose create partition. Now, similarly, let's create a partition for the other end. So choose this face and press on create partition. Now let's create another partition near the pipe junction, and this time we use the method as defined cutting plane. So what we're going to do is we are going to rotate this and we need to specify choose this again, press on done, choose point and normal, and we need to select the points uh, which is basically this point actually, and the edge is not the straight edge, which is this one, and press on create partition. So you can see this partition has been made as well, and similarly we create another partition with the same define cutting plane technique, and for that we select this the cells to partition, press on done, choose point and normal, and the point that we need to select is basically this one, and this is the select a normal direction, press on create partition. So we have made 4 partitions. Now from the main menu bar, go on to the mesh and controls. Uh, we have to assign the tet element to this region. So choose this region, press on done, choose tet from here as the element shape, press on OK. Now go back to mesh and controls, and we need to choose this region, this, and this region, and press on done. And over here, uh, we choose the sweep option and the middle axis as the algorithm. Press on OK. Now from the main menu bar, mesh and element type, and we select the whole model. Press on done. Over here, we need to choose uh, the heat transfer as the family, and uh, that's all. Press on OK and done from here. And from here, this one, seed part instance, and put the global size as 0.05. Press on OK and press on done. We go on to the tools, virtual topology and combined faces, and we select these three outer faces. Press on done and press on yes. Next, uh, we need to combine the three inner faces as well. So let's rotate it. So this face, and this face. Press on done. Now, uh, let's mesh uh, the part instance. Press on OK and press on yes. So now the part has been meshed. Now let's create a job and submit the job. You can name the job as pipe thermal. Continue and submit. Moving on to the visualization module after the job has been completed. So this is the undeformed shape plot. So we actually go on to this dialog box, to this field output dialog box over here, and choose NT11. So you can see the maximum values are represented by the red color, which shows the temperature distribution in the pipes. Now, since this thermal analysis is complete, now let's move on to the stress analysis. So we basically copy the thermal model and name this as stress. Press on OK. Now we can actually set this as the root, and over here we need to replace the heat transfer step with a static journal step. So in the steps container, choose replace, and over here choose static journal. Press on continue, and the time period can be 10, and the initial incrementation size is 1. Press on OK. Now we need to create an assembly set, and double click on set and name this as n-ist, which basically consists of the two vertices. So let's rotate it, and these two vertices, this, press on shift and choose the other vertex and press on done. So now in the history output, press on edit and request for the displacement outputs as well. Press on OK. Now we need to apply a pressure and go on to the load module and choose the pressure over here, and press on continue. So choose the internal surfaces, and for doing that we can actually choose angle option over here, and all the internal surfaces have been chosen, and press on done. So put the magnitude as 3.5 e to the power 6 and press on OK. Now let's define the boundary conditions. So double click on the boundary conditions and choose the step as initial. So first of all, we'll choose the we'll actually choose the type of selected step as symmetry, anti-symmetry, symmetry, and caster, and select the faces. So This will be our first boundary condition on this face. Press on done and choose the pinned option. Press on continue. So this face is the pinned face. Now let's choose the X symmetry faces. So double click on boundary conditions again and press on continue. Now select the faces on which we need to apply the boundary conditions. So this one, this, this one. These are all the symmetry faces. So we have selected the faces. Press on done and choose the X symmetry. Similarly, we need to also put the boundary condition uh, on the Z symmetry faces. So let's create another boundary condition. Press on continue. And first of all, let's select this face and then press on shift, this one, this one, and this one. Press on done and choose the Z symmetry. Press on OK. Now the boundary conditions have been applied. So we made 3 boundary conditions. Now we need to uh, change the element type assigned to the part regions. So what we do is we go on to the instances and over here let's choose the mesh. So now we are in the mesh module. So go on to the mesh, element type, select the entire model, press on done, and then over here we select the 3D stress. Keep this reduced integration toggle on, and that's all. Press on OK. Now we create a job, and in the job module, create a job, and we can name this as pipe stress. Since the job has been completed and we are in the visualization module, now we can actually put the contours on the deform shape, and here you can see the legend which represents the U magnitude values. And one thing you can do is you can change the scale factor. So if you go on to common options, and over here the deformation scale factor is right now 719. So you can change the scale factor from here. For example, if you choose 800 and apply, you will change the scale factor. So now let's move on to the next analysis, which is basically the restart analysis. Now let's copy the stress model and rename it as stress restart. Press on OK. So over here we go on to the steps and double click on it. So you can see it's static general like we selected before. So let's create another step and press on continue. Over here put the time period as 200 and implementation as 0.2, the initial implementation size. Press on OK. After creating the step, now we can modify the history output request for the set nhist. So what we're going to do is right click, press on edit over here, choose the domain as set, and over here nhist. So if we go on to the thermal option and choose the nodal temperature as an output request and press on OK. Now we go on to the predefined field in the model tree, double click on this and choose the second step and press on continue. So press on done over here, and in this dialog box We choose the distribution as from results or output database file, and we can choose the file from over here, which is the pipe thermal ODB file. Next, put the value for begin step as one, begin increment as one, end step as one, and the end increment as 100, and choose this as incompatible, and the relative value is 0.05, and press on OK. So we actually also need to edit the region, and let's select the entire model, press on done, press on OK. So now we double click on the stress restart model, and over here we toggle on the read data from job and write it as pipe stress dash stress. Just remember that the text input is case sensitive, and other than that we keep everything as it is, and press on OK. So yeah, we actually forgot to put in the step name, which is step dash one. Press on OK. Now let's create a job and name the job as pipe dash stress dash restart, and press on continue. And over here, so you can see the job type as restart. Press on OK. Now submit the job and wait for it to complete. So now the job has been completed, and in order to plot the contours for uh, Mrs. Stress, we choose the deform shape, and here you can see the stress distribution at the end of the analysis. Now let's move on to the final phase, which is the coupled thermal stress analysis. And to do that, we copy the stress model. So, so let's copy this model and name this as stress explicit. Press on OK. And now we replace uh, the step with a dynamic step, and this one, the dynamic temperature displacement explicit step. Press on continue, and over here the time period is 10 seconds, and press on OK. Now create another step, and which is also the temperature displacement explicit step, and for this put the time period as 200. Press on OK. So for both the steps, we need to apply the semi-automatic mass scaling. And to do that, double click on the first step, go on to the mass scaling, and over here, use scaling definitions below, press on create, and you can see the objective is semi-automatic mass scaling, and the scale factor should be 1 e to the power 8, and it should be for the whole model. Press on OK, and press on OK over here. Similarly for the second step as well. Press on OK and press on OK. So next we delete the history output request. Let's delete this. And now we resume the surface film conditions in step 2. So to do that, in the model tree, we expand the interactions container. And over here, select both the interactions, right click, and choose resume. So in the interaction manager, which is over here. We select each created field. So let's select the first one and choose the option move right. Similarly for the second one as well. Now, uh, we have to recall that in the dynamic analysis, loads are applied instantaneously. So, however, in this problem, a quasi-static response is sought. And for this purpose, we have to create a smooth step amplitude curve. So let's dismiss this and double click on it. Choose the smooth step option over here and press on continue. And in this dialog box, uh, put the first coordinate as 0, 0, and the next one as 10, 1, which basically will define the curve. Press on, press on OK. We edit the pressure load. So press on edit. And over here, we choose the amplitude curve as amp2 and press on OK. Now, the last step before creating a job is we change the element library to explicit. Uh, and to do that, let's go on to the mesh module, mesh, element type, choose the entire model, choose explicit over here, and the element family is to be coupled temperature displacement, and select the reduce integration over here. And so now we have the resulting hexahedral and tetrahedral element types. Press on OK, create a job, name this job as pipe stress explicit, and choose stress explicit over here. Now let's submit the job and wait for it to complete. So after the job completes, we can plot the contours for message stress, and like we did before.